All right, guys, today we're going to talk about 2.2, 2.3. We're going to combine a couple sections here. We're going to talk about complex numbers, what those are, their imaginary parts, and what an imaginary unit or imaginary number is. And then later on, we're going to talk about how to solve some problems similar to what we're going to start with here. So to introduce this idea that there are imaginary numbers, which is really just an unfortunate name, they do exist. And they're actually pretty useful, surprisingly enough. These are used a lot in electrical engineering. Okay, so let's say I gave you a problem like this to solve. Say in example 1, solve x squared equals 25. So of course, at its root, this is asking me what number times itself twice is 25. So there are two solutions to this. In fact, we'll talk more about the fundamental theorem of algebra later on. But anytime we're solving a quadratic, we should get two solutions. So most of you would know to go and do the square root, right? To get rid of the square off of x. But there are two solutions, positive 5 and negative 5. Both times themselves twice would get me to 25. So both positive 5 and negative 5, right? 5 times 5 or negative 5 times negative 5. It has two solutions. Okay, so if we look at example 2, which is a very similar problem, but now it's asking what times itself twice equals negative 25. Well, a positive times a positive is positive. A negative times a negative is positive. Is there any real number that times itself twice is negative 25? And there is no real number. Okay, so if we try to do the square root here, we get x equals a non-real number. There's no number on the real number line that satisfies this condition, that times itself twice would give me negative 25. Okay, but these computations do come up a lot in real practical situations. Like I said, electrical engineering, these actually come up a lot. So we needed a way to represent these negative numbers in square roots or even numbered roots. We'll talk about other roots later on. And so we've defined what's called the imaginary unit. And we use lowercase I. It has a little bit of curve like that. You can see a nice typed version of it here. Okay, lowercase I, do not use capital I for imaginary unit. And we've defined that to be equal to the square root of negative 1. So I is defined as the square root of negative 1. Okay, and that will give me something to represent these non-real values. In fact, we're going to figure out a way we can write the answer to this with our imaginary unit. So we can think of what we were trying to solve there, the square root of negative 25, as being equal to the square root of 25 times the square root of negative 1. And if we do that, simplifying, the square root of 25 would be 5. And the square root of negative 1 is defined to be I. So we can write this as 5i. Now, for our problem up here, where we needed to put plus or minus, we could write this as plus or minus 5i. Positive 5i and negative 5i would give us our two solutions there. Okay, so anytime we have a negative number in a square root, we're going to use I to represent that. And if we do have something like negative 25, we can separate that as that number times the square root of negative 1. So that number times I. And square root of 25, of course, gave us 5, and then we had I for our answer. Okay, but I itself isn't the only thing that will show up. There's lots of times where we're going to need to use or work with different powers of I. So we knew I from the previous page there is defined to be the square root of negative 1. But what if I do that value times itself twice? So in this case, we're actually going to write it with parentheses. If I do my work off to the side here, which we will erase in a second. But I squared, if we do that with parentheses, actually we can put it up here. The square root of negative 1 squared. And you can think of these square root and square functions as canceling each other out, and we end up with negative 1. Okay, if we did I to the third, that's like taking I squared which is -1, times another I, which is the square root of -1. So that's I squared times I again. That would give me I to the third. And this simplifies as the opposite of the square root of -1, or -I. This is just equal to -1, and this is, of course, I itself if I wanted to define it with I. Okay, I to the fourth power, though, would be, well, the easiest way to do this is actually to take I squared and square it. Properties of exponents say you multiply those exponents. So if I take I squared, which is -1, and square it, it gives us back +1. So these are the 4 different powers of I. And in fact, if you were to continue that pattern, I to the fourth times another I, which is equal to I to the fifth, I could take my answers of 1 and the definition of I, and I just get the square root of -1 or I back. That might have been a little bit confusing, but if I then multiply by another I, just like if I were here and I multiply by another I, we end up getting back -1. And if I multiply that by another I, we get back -I again. And if I multiply that by another I, we get back +1. And in fact, this pattern just continues. Okay, so it actually repeats every 4 powers of I. There's only 4 different states that I will ever be in if we simplify. So a nice way of visualizing that is this little chart over here on the right. So you can think of as we always start on kind of the positive x-axis. This will be important when we talk about trig as well. We always start over here. And we're going to go counterclockwise every time I multiply by I. So I times itself one time is I, right? I to the first power. I to the second power is -1. I to the third power is -I, and I to the fourth power, we're back at +1. Okay, so if you start here, every time we multiply by I, we go around, and it just kind of keeps going in this circular pattern over and over again. And it repeats itself every 4 times. So how can we use that to answer questions like these? How do I find these large powers of I? Okay, well, what I want to know is how many times, if I wanted to do I to the 63rd, I don't know that I want to count around this 1, 2, 3, 4, 5, 6, 7, 8, until I get to 63, right? I mean, that's bordering child abuse there. So instead, we want to find a faster way. So I know this thing repeats itself 1, 2, 3, every 4. So one question I ask myself is, how do I know how many times this would go through that, what we call 4 cycle? And I can figure that out by taking my number, 63, and dividing it by 4. Okay, 4 goes in there once. I'm doing this by hand. You probably don't need to do this by hand. It goes in there 5 times, which would be 20, and there would be a remainder of 3. Okay, so this tells me it goes through my 4 cycle 15 times, and this remainder of 3 would mean it needs to go 3 more steps. So it would need to go, after it goes through 15 times, it would go remainder 1, 2, 3. And that brings me to -I. In fact, I now know, as we have this little kind of column here, that if I have a remainder of 3, my value will give me -I. Okay, similarly, if I had a remainder of 2, we'd end up here. If I had a remainder of 1, we'd end up here. And if you should not have a remainder of 4 when you're dividing by 4. If you have a remainder of 0, then we are at 1. Okay, so let's try this next one. I to the 102nd. Let's figure out how many times it goes through our cycle up here by dividing it by 4, since our cycle repeats every 4. 4 goes into 10 twice. 2 times 4 is 8. 4 goes into 22 5 times. 4 times 5 is 20. And we'd have 2 left over. So it goes through my cycle 25 times, but then it needs to go 1, 2 more steps, which brings me to -1 I to the 102nd power is the same as just -1. Now, that's actually kind of cool. I didn't talk about it a second ago, but if you take some imaginaries times themselves multiple times, we can actually get real answers back. Okay, so next up, we're going to talk about complex numbers. And a complex number is really more broadly contains both a real and imaginary part. Okay, and it's of this form, a plus bi, where a is the real part of our value, and bi is the imaginary part. Okay, so a complex number has both a real and imaginary part. Now, sometimes the real might be 0, the imaginary might be 0i, but they always have a real and imaginary part. In fact, complex numbers encompass both real and imaginary numbers all together. It's a way of combining both. So let's go over an example. Okay, so let's say if I wrote this complex number, 5 minus 6i, identify the real and imaginary parts. Okay, well, the real part here is positive 5. And our imaginary part, and we keep the sign with it, is negative 6i. Your imaginary part should always have I with it. You do want to keep that sign in front. And our real part was positive 5. Okay, so hopefully pretty easy to identify those two parts. Let's talk about doing some operations. And, well, gosh, I'm not going to lie to you guys. This is really, really difficult. So buckle up. Make sure you're paying attention. This thing's going to get crazy here. We're going to talk about adding, subtracting, and multiplying complex numbers. So as a note, because for some reason this confuses a lot of people, the parentheses are only there to group complex numbers as a single unit in most of the cases. So just because you see parentheses doesn't mean you need to multiply or FOIL. In fact, we are just adding these two complex numbers. So we have this complex number, and we're adding them together. It even says add. Okay, so here's how we add complex numbers. Are you ready? We're going to start with the real, and we're going to add the real. 5 plus 3 is 8. Then we're going to come back for the imaginaries, negative 2i and positive 6i, and we're going to add the imaginaries, which gives us positive 4i. But we have to make sure the real is first and the imaginary is second. And there we go. 8 plus 4i. That's our answer. Pretty difficult, I know. Thank goodness. I'm glad you guys were paying attention. That could have gotten really difficult to explain otherwise. So let's try another one. Subtract. It's even helping you out. Do not multiply. We are subtracting these two things together. This complex number minus this complex number. Now, just like we did before, I do need to change this to adding the opposite or distribute my negative signs. That becomes negative 6 plus 8i. Sorry, having pen difficulty here. And there's nothing to distribute through the first set of parentheses. Okay, well, once again, let's take our real and combine them. Negative 7. Then we're going to take our imaginary and combine them. Positive 11i. And that is our answer. You write the real part first, imaginary second. There is our answer. I don't like that in green, sorry. That was a terrible box. We're going to have to come back and edit this. Maybe. Okay, I didn't edit that part out. Sorry for wasting your time. All right, next up, we need to multiply. This time, it actually is multiplying. They're directly next to each other. This is implying multiplication. And here's where a couple key things will be important. I need to remember what I squared, specifically, this will come up a lot, is equal to. So if you remember from our previous slide, I squared is equal to negative 1. Okay, we will use that. You should never have a power of I bigger than 1 in your answer. So I'll say that again. You should never have a power of I bigger than 1 in your answer. If you have an I squared, or an I to the third, or an I to the 17th, it is not simplified. I to the first should be the largest power of I in any answer. Okay, so let's go ahead and multiply. We do need to distribute like normal. This gives me 24i. 6i times negative 2i is negative 12i squared, I times I. And here's where I said you cannot leave a power of I bigger than 1 in an answer. However, we just talked about I squared is equivalent to negative 1. We get to substitute in. So we can replace I squared with negative 1. And hey, check this out. Negative 12 times negative 1 is positive 12. That becomes the real part of our answer. And this positive 24i is the imaginary. So it's tacked on with our I there. 12 plus 24i is the correct answer. Okay, let's try another example. Uh-oh. Hang on. Okay, let's try that now that this has its own room here. Now we need to multiply, and we do need to do kind of a FOIL, I guess, right, or double distribute. So let's do that quickly. 1 times 4 is 4. 1 times negative 3i is negative 3i. Distribute the negative 2i. That gives me negative 8i. And negative 2i times negative 3i is positive 6i squared. And once again, like we just talked about, should not leave a power of I that is greater than 1 in any of my answers. So we need to replace this with, why is that not changing colors? I don't know. We need to replace this with negative 1. So let's do that. That becomes 6 times negative 1. We'll go ahead in this step and combine these. I can see those are like terms. Negative 11i. Multiplying over here, we get negative 6. And actually, my two real terms give me negative 2 minus 11i. Remember, the real is written first. The imaginary is written second. Okay, let's try some more. Okay, so now it's asking us to use some of our knowledge to simplify radicals. Okay, the solving with square roots we'll get to in a bit. Right now we're just going to work on simplifying radicals with what we know about I. How do I simplify something that has a negative radical? Uh-oh, there we go. Apologies. So simplify each of the following. Square root of negative 40, we said earlier, I can separate this as the square root of negative 1 times the square root of 40, which means I can take an I out in front. So replacing that with I times the square root of 40. Now simplifying radicals, it might have been a little while, but you guys have definitely practiced this before in Algebra 1 and in geometry. So you want to do a factor pair tree or factor tree. You can do 4 times 10. 10 exists as 2 times 5, and 4 is 2 times 2. And you can look for pairs of factors, right? That's basically guaranteeing a perfect square there. So we get to take, this is basically the square root of 4, so we get to take a 2 out for our answer. There's an I also outside my radical, and that's usually written after our constant, so 2i. And inside my radical, anything that didn't have a pair, like these two, need to be multiplied back together. So 2i times the square root of 10 is our answer. Okay, so let's try our next example. The square root of 80, negative 80, I should say, over 2. So once again, you can think about simplifying the top as taking out the square root of negative 1 times the square root of 80 all over 2. So we're going to take an I out for our answer. I know for sure there's going to be an I outside my radical, right, from our square root of negative 1. I do need to simplify the square root of 80. So I might need a big factor tree here. 8 times 10, 2 times 5. That's 4 times 2, and our 4 becomes a pair of 2's. So anytime I find a pair, I can bring that outside of my radical. So a 2 from this pair and a 2 from this pair gives me 4. 2 times 2, or 4 on the outside. And the only thing left over without a pair is a 5. So far I have 4i root 5 all over 2. But because everything in the top and bottom is held with multiplication, we can cancel out common factors. So 4 and 2 can be reduced, and we simplify this all the way down to 2i root 5. Okay, one more example. Okay, so say we have 2 times the square root of negative 25 over 3. So once again, hopefully you're getting the idea. When I see a negative sign and a square root, I is going to come out for that negative sign. So you can think of this as 2 times the square root of negative 1 times the square root of 25 all over 3. So this is going to become I. Square root of 25 is going to simplify nicely for us. That's 5 over 3. And multiplying up top, we end up with 10I over 3. 10I thirds is our answer. Okay, last part of our lesson is to talk about how do we use this to help us solve quadratics. Specifically, we're going to look at quadratics if they were in that form ax squared plus bx plus c, the standard form, the ones that don't have a middle term. There is no x to the first power. If that is the case, solving with square roots is a very fast way of solving quadratics. So now that we have an idea what an imaginary number is, which will come up a lot, let's talk about how we can solve some of these quadratics with square roots. Okay, so I see, of course, in 13 here, we have a quadratic that has no x to the first power. So to solve this, we're just going to get x squared by itself by adding our 49 over. X squared equals 49, and then we can use square roots. So here, don't forget to put plus or minus. There are 2 solutions, and in this case, plus or minus 7 is our solution. No imaginary numbers needed yet. Okay, our second example here, x squared plus 64. Once again, there's no x to the first power, so we should be able to isolate x squared, get x squared by itself. We'll subtract over our 64, and then square root both sides. Okay, those will cancel each other out. Ooh, this time, though, we have a negative number in our square root. Well, now we know how to deal with that. I still need to put plus or minus, but we can think of this as the square root of negative 1 times the square root of 64. So we get plus or minus. This is going to give me 8, and this is going to give me I. Plus or minus 8I. There's our 2 solutions for x. We just needed an imaginary this time. Okay, 2 more examples. Our next one, again, there's no middle term with x to the first power. So I need to isolate x squared, and we can use square roots. So let's add 81 over. 4x squared equals 81. Divide by 4. So now I have x squared equals 81 fourths, and then we can square root both sides. Now, properties of radicals, and we didn't talk about this yet, but you can separate them over multiplication or division. Whoops, square root of 81 over the square root of 4, and it is plus or minus. So if we do that, luckily enough, these both give us nice answers. The square root of 81 gives us 9 in the top of our fraction, and the square root of 4 is 2. Plus or minus 9 halves are our 2 solutions. Okay, last one here. Again, no middle term, so we should be able to solve. Let's get x squared by itself by subtracting 16. Sorry, I should say solve with square roots. Negative 16. Divide away the 9. And then we can use square roots. Negative 16 ninths. And we square root both sides. So just like we said before, you can separate this as, and don't forget your plus or minus, the square root of the top over the square root of the bottom. Okay, radicals can be separated or combined over multiplication or division. Now up top, remember with that negative, you can think of that as square root of negative 1 times the square root of 16. So we get plus or minus, square root of 16 is exactly 4. That's going to give me an I, so we can write 4I up top. And the square root of 9 in the bottom is 3. 4 thirds I, or 4I over 3, plus or minus, are our 2 final solutions. Okay, so that's it for today. We're talking about complex numbers, which has half a real number and half an imaginary number. What an imaginary number is defined as the square root of negative 1. We talked about the 4 powers of I, which are important to know that cycles, and that hopefully that picture here with this guy swirling around, right, going around every 4, hopefully is a good visual to help remind you of where they go. You can think of this as being the real number line. This is actually called the complex plane, where it's complex numbers. So the reals go on the x-axis and the imaginaries go on the y-axis. It's a nice way of remembering that little chart.